a cubic spline. The most commonly used spline interpolation is of course the cubic spline interpolation formula. It takes care of the functional values, also the slope of the function, and also the curvature of the function at the breakpoints, that is the nodal points. We consider now the construction of a cubic spline function Sx for interpolating the n+1 points x0, y0, x1, y1, xn, yn, where no two xi's are the same. The cubic spline Sx should satisfy, as I have already mentioned, that first condition is Sx should belong to C2AB, that is twice continuously differentiable function on AB, and Sx consists of n-1 cubics corresponding to n-1 subintervals. This we may consider as the condition A. Also that we should have Sx must interpolates y at all the nodal points x0, x1 up to xn, so that S at x is equal to xi is equal to yi, I is equal to 0 to n, a total number of n+1 conditions. The second condition is adjoining cubic polynomial pieces Si and Si plus 1 must have the same value at the common knots. Knots means the nodal points, that is xi, that is Si at x is equal to xi should be equal to Si plus 1 at x is equal to xi for I is equal to 1, 2 up to n-1, that is the internal points, internal nodal points. We have thus another n-1 conditions. The next one is the first derivative. The first derivative at the intermediate knots must be equal, that is Si dash at the point x is equal to xi should be equal to Si plus 1 dash at x is equal to xi, I is equal to 1, 2 up to n-1. This is for the smoothness at the knot points. There is another n-1 conditions. And lastly, the second order derivatives also satisfy similar conditions at the interior points. Si double dash at x is equal to xi should be equal to Si plus 1 double dash at x is equal to xi, I is equal to 1 to 2 up to n-1, that is for maintaining the curvature condition at the nodal points. There are n-1 conditions. So altogether we have n plus 1 plus n-1 plus n-1 plus n-1, altogether 2n-2 conditions. But note that each of SIX contains 4 unknowns. Note that SIs are cubic polynomials, so it involves 4 unknown components, 4 unknown coefficients. Si contains 4 unknowns. Since SIX are cubic polynomials, there are n number of subintervals, so we have to determine altogether 4n number of unknowns for finding out the cubic spline function Sx. This indicates that we require still 2 more conditions for determining the 4n number of unknown coefficients uniquely. One of the following conditions, known as the n condition, may also be chosen as the additional condition. At the end point, we may have, at end point, that is the left hand point at x is equal to a, we may have s dash a is equal to y0 dash, and at the right hand end point, that is s at x is equal to b, we may have s dash at s is equal to b may equal to the yn dash. This condition is known as clamped condition. Alternatively, we may consider natural cubic spline, so that at the left hand end point x is equal to a, s double dash at x is equal to a is equal to 0, and s double dash at x is equal to b is also equal to 0. There is another alternatives when the exact function fx is known to be a periodic function with period xn minus x0, so is Sx. Then in such cases we may take S1 x0 is equal to Sn xn, S1 dash x0 is equal to Sn xn, and S1 double dash x0 is equal to Sn double dash xn. So with the 4n conditions and taking any one of the conditions C marked as C, any one of the condition marked as C, we will get altogether 4n minus 2 plus 2, that is 4n conditions. With the help of these 4n conditions, we can determine the 4n number of unknown coefficients required for determining uniquely the cubic spline polynomial function Sx. So in this way, we can determine the cubic spline polynomial Sx uniquely, which will take care of the value of the function at the nodal points, the value of the derivatives of the function at the nodal points, and as well as the value of the second order derivative, that is the curvature of the function at the nodal points. Thank you very much.